Welcome to the first exploration video. This video will introduce the explorations. A second video will go through the solutions. Both the explorations and the solutions will also be available as a PDF file. Successfully completing this small collection of explorations will presuppose a complete understanding of all the topics of Lesson 1, while simultaneously introducing you to the topics of Lesson 2. They're designed to show you how the concepts we will discuss in Lesson 2 arise naturally from the axioms. I hope you enjoy them. Aspiration 1 asks you to consider the following objects. How many ways can you arrange two arrows among these objects, one between A and B and another between B and C, to form a partial triangle? Number your diagrams and name the arrows F and G. B. Complete all those partial triangles the theory tells you can complete. Give the name of the arrow that you have drawn. Every construct in Lesson 2 will be based on one of the diagrams that you cannot automatically complete. When you complete this problem, consider the structures of the partial triangles you couldn't complete. They should remind you of two structures we discussed in Lesson 1. In the solution video, I will discuss what this means about the nature of structure and abstraction in category theory. Aspiration 2 has many parts. The first few are trivial and just ensure that you have absorbed the material from Lesson 1. The second half of the aspiration, however, will introduce you to two important concepts. The first is the general concept of the Algebra of Arrows. If you had to give category theory a tagline, that would be it. You are introduced to this through a determination problem, also called an extension problem. The second is a specific case of the Algebra of Arrows, and that is representing the system of arrows as a commutative diagram. This exploration will be concerned with sets A isomorphic to 2 and B isomorphic to 3. The first 5 parts are trivial. Part A asks you to number the maps A to A, or for the number of maps A to A. B for the assignment equation of those maps, and C for the mapping graphs. D prepares you for the determination problem by presenting its degenerate case. In other words, we could rephrase this question as, given F and 1A, what are all the maps G from A to B such that the diagram commutes? E introduces the two functions that the rest of the exploration will be concerned with and asks you to draw their map graphs. And then F says, consider all maps alpha I from A to A. For each alpha I, can you find a map G not equal to F0 such that the following diagram commutes? For each alpha I, if you can't, explain why not. If you can, draw the mapping graph of all such G. Describe the relationship between F0 and all the maps G you have found. We can say that G has been transformed into F0 through the action of alpha I. What name would you give to this action? Example, alpha I is the blank map. These determination problems are the core of science, as we shall see in Lesson 2 when we study real examples. For now, we can just notice that once we find G, that F0 is not really that important anymore. F0 is just a composite of G following alpha I. If we don't have any solutions G, then maybe F0 and alpha I observe different things about the system. The reason why this is the core of science is, well, this is what science generally aims to do. Given the collections of observables in one system, can we find the core observables? i.e., can we figure out which observables determine the other observables in the system? Part G asks the same thing but for F1, and they both ask you to name the map alpha I. Successfully completing F and G will make H trivial, but following our analogy, it will show that alpha K is determined by alpha J and alpha I. Remember I talked about structure and map objects? We will learn that not all maps are created equal. Some maps serve as generators for other maps. And one question we immediately want to ask then is, what is the minimum number of maps that we need to specify a certain collection of maps? And that is a very interesting question with a very interesting answer. I hints at it by asking you, given a fixed alpha I and alpha J of your choosing, and by the time you get to this part it will be obvious what these maps should be. How many diagrams with a unique FK do you need to specify with all the G and H that make the diagram commute, all the maps A to B? And here's a bonus question. I claim that by fixing FK, alpha I, and alpha J, and then by adding one more arrow to this diagram, it will allow you to encode all the maps A to B under the action of the new arrow, with just this one diagram. Describe that arrow for me. Just give me this assignment. And consider the 3 FKs you found. That will give you a clue. And finally, for Aspiration 2, I introduce you to the concept of idempotence and involutions. Just a little hint of two concepts that will become important to us in the future. So having completed Aspiration 2, Aspiration 3, 4, and 5 should be easier than if you had not completed Aspiration 2. 3 asks you to form a definition of the equality of maps using the terminal object. 4 asks you to use the terminal object and cluster types to describe the structure of any map F that satisfies the following condition. If F following G1 is equal to F following G2, then G1 is equal to G2. Aspiration 5 tests your intuition for the opposite category. It asks you to take your diagram from Aspiration 4 and imagine it as an object in SOP. It then asks you to describe the nature of F in SOP, and then use that knowledge to form a condition that the corresponding S map H must satisfy to have the same property. And that's it. These aspirations should prepare you for Lesson 2, where you'll be introduced to many concepts that on the surface may seem different, but they all relate to those 2 partial triangles you couldn't complete, extensions and liftings, or determination and choice, and to the structure of the relationship of maps in S. If you successfully complete these aspirations, you will have no problem with material in Lesson 2. If you have any issues, you can discuss it in the group, or link me on Twitter at Codrington, and I'll see you in the solutions video.